Hi, Amy. How are you doing?
Hi, sir. I'm good, thank you. How are you?
I'm fine, thank you. So,
Good.
I heard that you're having a lot of difficulties in understanding these basic concepts of mechanics. How do you feel this subject
Yes,
is
for
for
sure.
you?
Not good. Definitely finding it much harder because, like you said before, it's more physicsy, and I'm just not a fan of physics. So, yeah, I'm definitely finding this way trickier than like the pure side. But on the bright side, on the pure side of my thing with the teacher and stuff, I'm like flying through it. So,
Very
but
good.
it would be nice to fly through both of the sections. So
That is so
yeah,
true.
with your help, hopefully.
What level of physics have you done, Amy, so far?
Just like the basic, GCSE year 10
Hmm.
physics. But
Okay.
whenever I got at the end of my GCSEs, I got a fairly good grade. But the only reason was because of all the maths that I was good at. The actual physics content I didn't understand, so
Oh,
I kind of like skimmed
right.
past that.
So,
Yeah.
okay. So, while explaining you the concepts of mechanics, I'll keep that in mind and that should help. So what I've done
Okay.
here is for today's lesson, we are actually introducing you to coefficient of friction, Newton's second law. These are very difficult topics to deal with, and you should
Mm.
be good with all those five, six formulas which you learned about velocity, acceleration, displacement, relationships. Okay,
Right.
so
Yeah.
it's going to link everything which you've learned so far. So let me just share with you the lesson which I have prepared, and to make it very interesting, I've taken up an example from our daily lives. You know, these days of
Uh,
COVID, we are kind of bound in our own houses and we are never going outside, going only
right.
for essential things. So, for example, shopping, I just go once a week. And after a very long time, I started liking shopping, rather loving it. So,
Yeah.
when I
Yeah.
go once, I look at things very carefully. So, during my last visit to a grocery store, I came across this situation and I thought about the problem. So, today's lesson, I will take this grocery cart, and with that cart, we'll try to understand how do we understand the physics of it and how do we relate it with mathematical modeling. So, that is kind of interesting,
Oh,
right?
yeah.
So, I hope you that will help you since for you also, physics is challenging, right? We'll actually
Yeah.
elaborate on the Newton's second law of motion, understand what is this concept. And from the concept of Newton's second law of motion, we actually come to know also about equilibrium and non equilibrium situations. And basically, the law relates force with mass and acceleration. We'll look into that. To solve any problem, as you know, and you have seen earlier also, free body diagrams are required, and it's always good to take some applications from real life. So for today, the application is
Yeah.
based on this trolley car, and we'll see how does it work out. These are the three questions which we are going to look into. I have actually written the questions in a very short form, hurriedly, as it came to my mind. The very first one here is uh, let me give you the background on this. The background is kind of a new shopping center and a new store is coming up there. So, a new grocery store is coming up and they want to design their trolleys in such a way that they are efficient and they go with minimum damage. What they have seen earlier is that kids are playing around, they will just throw the cart and it will topple so many things and there's
Right.
a lot of losses. They want
Mhm.
to actually cut down on the losses and make the environment safer for all their customers. So that's the
Yeah.
idea, right? So for this safe environment shopping center. Okay, so what they found is that normally these cars are being driven uh, or pushed with a velocity of 2 meters per second. So they are saying that we need a car where cars with maximum of 1.5 meters stopping distance. That means if it is being pushed and left, in that case, it should stop within 1.5 meters, right? So that
All
it
right.
doesn't really go
Okay.
far or hit so strongly all the objects in between. So the idea here is we are looking for cars with maximum 1.5 meters stopping distance when it is moving at 2 meters per second. So that's the requirement, right?
Hmm.
Find the minimum effective coefficient of friction. So coefficient of friction is what we need to find between the wheel and the floor of the area. That is the question number one. Question number
Right.
two. So in question number one, as we'll go through this example, we'll figure out that this value of mu is 0.136. Well, what is mu? Coefficient of friction is mu. I'll elaborate on this later. Okay. So cart with
Okay.
the
Yeah.
coefficient of friction 0.136 has these properties. That is, if you leave the cart which is moving at 2 meters per second, it will stop within 1.5 meters. Okay. Now,
Mm-hmm.
with this cart, what can be the maximum slope of the ramp so that the carts stay in their position when left on the ramp? Well, this idea comes because stores want to really optimize their space. So to store their
Right.
carts, they know they are buying a cart which has a lot of friction. So why not store them
Mm-hmm.
on an inclined plane? They can now stack up many carts in the same area, right?
Oh,
The slope gives them
right.
additional length. So they want
Yeah.
to figure out what could be this additional length, right? This is one thing. Secondly, what I observed is everybody, I should say 99% of the customers were actually pushing the cart. But from my knowledge, I think pulling was important. So I introduced another question here. Anil moves the cart with constant velocity of 1.5 meters per second with a load of
Mm-hmm.
20 kg. What force is required to push or pull the cart at an angle of 30 degrees? So when you push the cart, definitely it is at an angle. So with the horizontal, if the angle is 30 degrees, what is the force required to push it? This is part one of the question.
Right.
Second is, if you want to pull it at the same angle, what is the force
Mm-hmm.
required? You can compare the two forces and figure out which is better
Oh,
situation, right? You'll be surprised. What do you
right.
think is better, pushing or pulling?
Um, I mean, I'm just gonna say by what I think. Like, if it was really heavy, the cart, I would to move the direction. I usually do pull and then push it the other way.
Push it the other way.
So
So you
yeah,
will be
I don't
surprised,
know.
pulling is much better, right? So we'll begin with the Newton's second law and then work
Okay.
on all these examples later. So Newton's second law, can you please, Amy, read all this?
Yeah. So the acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to its mass. The direction of acceleration is in the direction of the net force acting on the object.
Correct. So it is a vector quantity. It has magnitude and direction. Magnitude is proportional to the sum of all the forces acting at a point, and the direction is the direction of the net force. Now, what is the
Right.
net
Yeah.
force? At a point, if there are many forces existing, you simply write them in terms of x and y directions, right? So think like a coordinate plane, x, y axis. So if this is a force F acting, let us say this is the force F1. In that case, you can write this as a F1x and F1y, the two components along x and y direction. Let's say there's another force F2 acting at a point. This could also be written as a component F2x in x direction, F2y in y direction. So those are all the forces acting at a particular point. Now to find the sum of forces, add all the x direction forces and add all the y direction. So you get sigma of f of x, sigma of f of y. To find the magnitude, it will be square of these two, add them up. And to find the
Mhm.
angle, tan theta is rise over run. In this case, y component over the x component gives you the angle of the resultant force, correct? So that becomes a kind of summary of
Yeah.
what you have already done. Okay, so that is the meaning of the numerator, which is sigma f. Now I could actually rearrange this particular equation, multiplying by m, I get my equation that the net force. So this sigma f, we sometimes, most of the time, in fact, will write F net force, right? So the net force is equal to MA. MA means mass into acceleration, correct? So mass is constant.
Mm.
Acceleration is something which is varying. So if the force is large, more acceleration, less force. Less acceleration, zero force, zero
Right.
acceleration, correct? So a body at rest will have zero acceleration, correct? So it
Hmm.
all depends on the net force. So if there is, you can also say if acceleration is equal to zero, it means what? It means that the net force is Zero. Is it clear to you? This also means that
Yeah.
if acceleration is zero, then the net force is zero. Now, if the cart is moving at a constant speed of 2 meters per second, in that case, is acceleration zero?
I'm gonna think it's no, but then you're gonna say it's yes.
Yes, yes, it is yes. Because constant
Oh,
speed,
I don't get that.
constant speed means no acceleration. Rate of change of velocity is acceleration, right? Now, constant
Right.
velocity
Yeah.
means no acceleration, right? So acceleration is zero. So if I say
Um.
that I am
Okay.
moving a cart with a constant velocity, it means zero acceleration. That means net force is zero.
Oh,
Do you
okay.
understand this concept?
Right. Yeah. 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 That's
Very
actually
important to
clear.
understand.
Mm-hmm.
Correct. So now, will you please read this part?
Yeah. So Anil moves a cart with mass of 15 kg at a constant velocity.
Hmm.
The cart is moving at a constant velocity. Acceleration is therefore zero.
Correct.
Net
Very important.
force
Hmm.
F equals. Yeah. Yeah. Oh, so should I carry on?
Yeah, carry on.
Yeah. Net force F equals ma means acceleration is zero. Therefore, the force is zero.
Correct.
So yeah, the net force is also zero. System is in equilibrium as the net external force is zero. Oh,
Perfect.
okay.
So when we talk about equilibrium and not equilibrium, equilibrium system means that the net force is zero. Get the concept.
Uh,
So
yeah,
when we are
yeah.
moving an object with constant velocity, even that system is
Acceleration is
equilibrium
zero.
because the net
Oh,
force is zero. You get the concept. Very
yeah.
important question. Most of the
I would
students.
never, yeah, thought that because I'm thinking when I think equilibrium, I'm thinking something is stationary in
Yes,
one position because all the forces are the same. I would never think of a moving object at equilibrium. So yeah, that's clear now because it's moving at a constant velocity
perfect. Read this
and the
part.
acceleration is zero. Okay. So system is in equilibrium means that the object is at rest or moving at a constant velocity.
Yes.
Oh, okay.
Very important, right? So this is what we should see Newton's second law as, right? It really relates to this.
Yeah.
Now let's look into our three questions. Question number one. Okay. Stopping distance of a car. This is a primary area of question number one is to think about what should be the coefficient of friction between the wheel and the floor so that we have the required stopping distance. Now this question is very important. We have asked this question so many times in different ways. For example, while you're driving a car, you just push the brakes because you want to stop the car within some meters, right? Or sometimes you push the brake
Right.
and you're unable to stop the car within so many meters. So it is very much related to all those kinds of questions. But I've taken a very
Oh,
interesting example of a cart and the shopping center or the grocery store. So can you please read this
okay.
question?
Yeah. So a grocery store wants to purchase carts for the store with maximum 1.5 meters stopping distance when it is moving at a 2 meter per second on the horizontal floor. Find the minimum effective coefficient of friction between the wheels and the floor to meet the objective.
Correct. So this is the question
Mhm.
for us, is a design problem, real application for a grocery store. So we will actually make a force diagram and then we'll write the related equations. So here is my diagram. So here is the cart, which we'll consider to be a point. The whole weight
Okay.
of the cart acts at this particular point and is normal to the floor. I mean, downwards. Mg is the force which is acting downwards, which is because of the weight of the
Right.
cart. Now, the normal is the reaction of this, we call this as F normal. F normal is the up, right angle perpendicular upward force, right? And these two forces are
Mhm.
equal. They have to cancel because your card is not jumping up and down. Is that okay? Fn
Yeah.
is equals to
Yeah.
Fg, right? So we got this. The
Yeah.
Fn is equal to the downward force, which is mg. Now, if you're trying to push the cart right, in that case, friction will always oppose the movement. So Ff
Right.
is the frictional force. So you need to apply some minimum
Mm.
force to push it forward. That is F of x,
Right.
right? So till you apply that much, the system is not moving at all. At that point,
Right.
it is Ff, the same. force. And this force is equal to mu times F of n. Always F frictional force is equal to mu times F of n, where mu is the coefficient of friction.
Oh,
Always.
okay.
So you have to find F of
So,
n, normal force. Normal force into mu, the coefficient of friction, is the frictional force for all our examples in physics. All our examples.
oh,
In this
all right.
case, yeah, simple. In this case, Fn is mg, and therefore the frictional force is mu
Mm.
times mg. Do you understand this concept?
Yeah, yeah.
Very
I think I actually do. Yeah.
Now
So,
we'll
yeah, so
begin.
what you're saying is, oh,
Yeah.
I was just trying to say what you're
Yeah,
saying
yeah,
was
say,
that,
say, yeah,
so
yeah.
these two, just like a quick summary. So
Yes,
like the force acting upward on the cart is the same as the like the weight of it, because it's the
yes,
reaction force, the normal reaction,
yes,
since it's like standing still. And then to find the net force, yeah, or is
yes.
it the normal
Network.
force?
Hmm.
Oh, net force. Yeah, you have to do the mass times gravity. So that's when you wrote Fn equals mg.
Yeah,
And then whenever you're trying to push something, obviously a frictional force will be acting in the opposite direction.
yes,
So then that's when you bring in the coefficient of friction, which is
yes.
where you put the mu there. Okay. Sorry, these terms are kind of new to me, so I was just trying to recollect what you said.
Sure.
So, okay,
So this
I'm following
coefficient
you.
of friction is also called the static friction. So we have two types of
Oh,
coefficients of friction. It is always more force applied to just move the cart, but once the cart is moving, then there's lesser force
mhm,
required. So that is
right.
dynamic coefficient of friction, right? But we'll
Okay.
restrict our examples today to static coefficient of friction. The idea is to understand the concept,
Okay.
right? Not to complicate
Right. Right.
to that extent now. We can
Yeah.
always do it later, okay? So all our friction
Yeah.
today will be static, okay? But the object
Okay.
is going to move. When it moves, we'll consider the same friction in two cases. Is that okay? There's always
Yeah.
very minor difference between the two. Anyway, so what you have understood here and what you were trying to tell me is this. Can you please read this part?
The vertical force will cancel out for the cart moving on the horizontal floor. So, oh yeah, so that's what you were saying. Yeah. Fn equals mg.
Correct,
So force of friction is the net force that will stop the cart.
correct. Well, in our case, the cart is moving at a constant velocity of 2 meters per second. We want to stop this within a distance of 1.5 meters, right? The only force which is acting to stop it is the frictional force, which is acting against the
Right.
direction. Therefore, the net force is F of F, the frictional force, correct? As far
Yeah.
as the Newton's second law goes, we know acceleration is the net force over the mass, right? Acceleration is net
Hmm.
force over the mass. Net force is the frictional force acting in the opposite direction. So I put minus there for it, right? So we know frictional
Oh,
force is
right.
mu mg. Substituting mu mg for frictional force, and m is in the denominator, m and m cancel. And so we get an acceleration of minus mu g. That means deceleration. Object is trying to stop.
Yeah.
Okay?
Hmm.
So we get very simple
Yeah.
relation, A equals to minus mu g. Now, we know that the stopping distance is given to us as 1.5 meters. We also know initial velocity is 2 meters per second. When it stops, final velocity will be zero. And the
Zero.
acceleration we just calculated is minus mu g. Going back to your formulas, which one will you apply? V square minus u square
You
is
square.
2as.
Oh, yeah.
Do you see how it connects with your first unit? So you
Hmm.
have to actually
With the
recall.
suva.
Yes, you
Yeah.
have to
So you can't
recall
just
and
like
put them
forget
all
that.
together. And
Right.
actually
Yeah.
put all the values. So v square minus u square is 2as. A is minus mu g, correct?
Hmm.
So I
So you
wrote
sub that
minus
in.
mu g here, and then I substituted all the given values. And actually, I isolated mu first. V square minus u square divided by 2gs. That's the formula now, right? It's a very
Right.
important formula for you. You can always make a note. When you rearrange all this, minus of, or better to go with the steps as shown here. But anyway, so substitute all
Hmm.
the values and calculate. Now, it is important that we are working to three significant figures, right? Since we are
Oh, because all the values they provided.
your
Yeah.
answer should be to three significant figures. And it is
Right.
0.136. No units. It is a ratio, right? No units.
Mhm.
0.136 is the coefficient of friction for this particular system. Is that clear to you?
Yeah, yeah,
What you also notice is stopping distance is independent of the mass on the card. Whether I put 20 or 50 kg on the card, it doesn't really matter. There is no m in this
yeah.
formula. Do you see that? Mu, the
Right.
formula which you have got.
Yeah,
There is no mass here, correct? Mass cancels away.
yeah.
So it is independent. Therefore, whether the
Oh,
trolley is empty or loaded, mu is
it
same.
will.
You get the idea?
Oh,
Mu is
okay.
same. Right?
Yeah, yeah.
So have you understood this solution?
Yeah, yeah, I have. So, would questions in my book, because I haven't seen this mu thing in my like book, but can I still use it
No, no,
in?
no. Whenever they
Oh,
talk about friction, you have to go to the next chapter in that case. So you are still in the first part of
oh,
it, where they are assuming that there
right.
is no friction between the two bodies, right?
Okay,
So
yeah.
what I like to show you the examples which you are talking about. You have seen the cases where the two masses, for example, connected on a table, and you assume there is no friction between them. In that case, as we
Right.
did earlier, we found that these are the accelerations and the tensions in the string, right?
Yeah,
We
yeah.
also took up an example where one mass was on the table, the other was hanging with a pulley, and we derived at acceleration and tension. And we also took up an example with the pulley. So you're talking about this in all these three examples, there was no friction
Mm.
in the question, and therefore mu was not there. So now in the next
But
part, yes,
yeah, it's just that in a couple of the books questions in my book, but the ones I did with you had no friction in it. That's why all these formulas worked. But some of the questions in my book, yeah, like that, there'll be one acting like that. So there, do I use mu?
then the net force Fp minus frictional force, just change it. So the net force will be friction
Oh,
force opposing in the opposite direction. Just do Fp minus Ff, friction force. So change
so
the,
if I was trying to
yeah,
use the tension one, you just do M2
yeah.
times
Replace
FP
F,
minus F of
yeah,
F.
yeah, yeah, yeah. So your force will now be
Oh,
Fp minus F frictional force. That is all. Otherwise, it is same.
all right.
And what is F of F? Yeah, it is mu
The
times
mu
F of N.
mg.
mg, right? Done.
Oh,
So that
okay.
is the
I
connection.
get it now.
Now you get it?
Oh, yeah. You made that really clear, sir. Thank you. Yeah, yeah, yeah. That's
My
clear
pleasure, my
now.
pleasure. So fortunately, I had these examples which we discussed in last
Right.
session, right? Okay. Now let's move on to question number 2. Can you please read question number 2?
Yeah. So the carts in a grocery store has effective coefficient of friction between the wheels and the floor as 0.136. A ramp is designed to hold the empty carts. What can be the maximum slope of the ramp so that the carts stay in their position when left on the ramp?
Correct. So this is a very interesting example because in the book we have only 3 types of examples, right? One is relating the motion with the friction and force and mass and acceleration, all those things. The other is inclined plane. So many questions are based on inclined plane. So I thought, let me just go ahead with this card and look into this concept also. So now
Right.
we are trying to put the card on an inclined plane and we don't want it to move backwards. It got damage and accidents, right? We don't want that in a safe store.
Yeah.
Now, when you put it in the inclined plane, in that case, the normal will be at 90 degrees to the inclined plane, correct? So this angle normal means 90 degrees,
Yeah.
correct? But the weight acts downwards as shown here, correct? If the inclined plane angle is theta, then this angle here is also theta, correct? Because this is 90 minus theta,
Oh, yeah.
correct? So this angle is also theta. Let me write down.
But isn't FN supposed to, is it just me or does it have to be a little bit straighter, the FN
You know,
line?
I mean, I have drawn a line which is slightly more inclined, but on
Oh,
a
okay.
inclined plane,
Just checking. Yeah.
no, it has to be Fn. This has to be 90 degrees.
Yeah.
This is Fn.
Right.
Is it okay? And
So
this
weight is acting
mg
like
cos,
this.
this is mg cos theta, and weight is acting downwards.
Oh, right. Cool, cool.
And this is mg sin theta.
Yeah.
So that is what I've drawn here on the inclined plane. it is mg sine theta, or weight times sine theta, which is the downward force, which is actually bringing it down. We want enough friction so that they
Oh,
cancel out. And so the cart will not move downwards. That is the whole concept.
right.
Correct.
Yeah, yeah.
And therefore, from here, we can actually solve the question. So basically, this is not required. Okay. So F cos theta is equals to Fn, right? These two forces cancel out, correct?
Yeah,
Therefore, F cos theta
yeah.
is Fn. So we know what Fn is. Fn, the normal force, is W cos theta, right?
Mm-hmm.
Now, this force, F sine theta, is equal to the friction force for these carts to stay in their position, right?
Frictional force. Yeah,
They
yeah.
are equal. Now, frictional force is always mu times the normal force, Fn. Frictional
Yeah.
force is mu times Fn. So from here, we can now find the ratio of these two. Fn and Fn will cancel.
Oh,
W sine theta divided by W cos theta, right?
it's tan.
Let's say this is equation 1, this is equation 2, right? Let me do equation 1
Yeah.
over 2. Okay. So W sine theta over W cos theta is mu Fn over Fn. So Fn, Fn cancel. We know what mu is,
Right.
0.136. Substitute the value. Sine theta over cos theta is tan theta. Tan theta is the value of
Where did
friction
the
force.
W go?
Cancel, cancel.
Oh, okay. So that cancels as well then. All right.
Yes.
Okay.
So this
No, I was
slope,
just thinking of it. If it was numbers,
yeah,
if it was numbers like 2 times 5 and then 2 times 7,
they
do
will
the
all
twos
cancel.
cancel?
Yeah, W is the W is
Oh,
mg. W is mg, right?
oh, right.
Weight
Oh,
is
okay.
W.
Yeah, yeah,
Instead
yeah.
of writing mg, I wrote W. Weight. Weight is the force. Okay.
Mm-hmm. Yeah.
So tan theta is basically equal to mu. Do you see the relation? So if you want to check what the angle
Oh,
is, easy. Equate it to mu. Done. We know what the angle is. Tan inverse of mu.
that was, oh my God. That was so good. Yeah. Okay. That's so clear. Right. So if I ever see a question, at least I know the relation. I can just go straight to it.
Yes,
But
correct.
it's definitely really good to see how you derive that. Yeah.
By definition, that is what mu
Mm.
is, frictional force. If you put a
Oh,
book on a table and you want to
right.
tilt the table, to what angle can you tilt? It only depends on the coefficient of friction, and you can actually calculate the
Oh,
value.
yeah.
So without doing anything, you
Yeah.
just measure the angle when it starts sliding. So as soon as it starts
Oh,
sliding,
that makes
tan
sense.
theta,
Yeah.
tan theta is mu, done. You don't even have to do any other calculation.
Oh,
You get the point.
right. Yeah. But logically, that makes sense. Yeah. Yeah. Because you're trying to find out what is the angle such that that object would stay without sliding
Without
down. So that the
sliding.
friction. Yeah. So
Yes,
that's the
this
point.
is the
Okay.
concept behind mu. Do you understand the coefficient of friction now?
Mm.
To what?
Yeah.
For
Yeah.
example,
Definitely.
there is a dump truck which has a lot of things, right? Now they want to just dump the sand, so they will actually do this angle. How much should be the angle so that it
Mhm.
doesn't slide? Tan theta equals to mu. Done. Question.
Oh.
You get my point.
Yeah.
So
Yeah. Yeah.
understand the concept. Many questions become very simple. So we
Right.
find
Yeah.
mu.
Yeah.
You see that now?
Yeah.
Good.
I can.
So the angle,
I
so
like
this
that
force
one.
could be 7.74 degrees. Do you see? It's enough. 7 degrees is quite a bit.
Mm.
When you make a slope on the floor, 7 degrees is very good.
Yeah. Yeah.
So with
And
this,
so that's the enough. That's the enough. Yeah, to hold the ramp, to hold the trolley. Yeah, so
trolley.
it doesn't move.
Question number
Wow.
3. Can you please read this one also now?
Yeah. So the carts in a grocery store has effective coefficient of friction between the wheels and the floor as 0.136. Anil moves the cart with constant velocity of 1.5 meters per second with load of 20 kg. What force is required if he pushes the cart at an angle of 30 degrees below horizontal or pulls the cart at an angle of 30 degrees above the horizontal?
Correct. This is also a very common example, push or pull. So we have seen the inclined plane. Now we'll just see on the floor, inclined pushing, force angles. Correct. So I've drawn
Okay,
the
yeah.
diagrams here. You should take a moment to understand these diagrams. How should we be drawing it? So first one is for
Yeah.
pushing. Pushing downwards means something like this, right? So this force will be resolved into two components, one along the x, one along the y direction. So this force F is resolved along the x and y direction. Theta, 30 degrees, is the angle between the floor and this angle of pushing. The horizontal component here is f cos theta adjacent, and this vertical component is f sine theta, right? 30 being the angle theta, right? So you can write theta, later on change to 30 degrees or whatever is in the equation. So you can actually have a general solution.
Wait, how come the always the x-axis is sine theta, and then no, sorry, the y-axis is always sine theta and the x-axis is
this
cos.
side is opposite, right?
Yeah.
Sine is ratio opposite to hypotenuse, right?
O over h.
H is force F.
Yeah. So how does that mean that one is sine theta?
Sine theta is opposite, so cut over. Sine is opposite over hypotenuse, cos adjacent over hypotenuse, right? Tan opposite over adjacent.
Yeah.
So we are using these ratios, right? So sine is opposite over hypotenuse. You write like this. You can write sine theta is equal to f of y over f, right? So in that case, cross multiply. F of y is equals to f times sine theta. So this, because it's acting down, this is your. Similarly, you could cos theta equals to f of x over f, and therefore f of x is equals to f times cos theta. Is that clear to you? For this particular diagram. Don't confuse yourself with the inclined plane, okay? Because inclined plane, the theta was like this. Do you see theta was here? So it's a different position. Therefore, the positions have changed. You see? So the movement this time is because of f cos theta. Okay? So when you're trying to push, when you're trying to push, the friction acts in the opposite direction. As I said, friction is always mu times the normal force. And the normal force is same as mg.
Right.
So we got f of friction as mu n in this particular case. Do you see that? So while pushing, that is our free body diagram. But when you pull, in that case, you will see that f sine theta is acting upwards, not along the weight. It is acting in the opposite direction. It is not adding to the weight. Since it is acting, it will neutralize some of it, right?
Yeah.
Therefore, it is easier to pull.
Yeah.
Therefore, it is easier to pull because this is helping you reduce this.
Right.
Frictional force still being the same. It is same as mu n, mu times mg. Frictional force is same. Do you see this? Now let's do our calculations and find the answer.
So
yeah. Yes, Amy.
Yeah.
Yeah. What do you have any questions, Amy?
Yeah, it was just with the push one, is the friction greater? So is that why it's harder? Whereas with the pull,
friction is same. The only thing is this force, vertical force. One vertical force is acting downwards, which is for push, and the other vertical force is acting upwards, which is for pull. When you pull, it is acting upwards, right? So it makes this effect lower.
Makes it easier.
Easier.
Yeah.
That's the reason.
Oh, right.
Now let's do the
calculation. So friction's the same. Yeah, it's the upwards and downwards. Yeah.
So here in this particular
example,
what we have figured out is that the force of friction is equals to mu times the normal force, right? I used n this time as normal force, right? So, and the normal force is, and this is F cos theta. Frictional force is equals to F cos theta, right? F is the force which we have applied at an angle of 30 degrees. Now, we can rearrange this equation and we can write, and second value is, now we know that this n is equals to mg plus f sine theta. Because this normal force is sum of these two forces, correct?
mg plus sine theta.
Normal force is these two forces. Do you see that? F sine theta. Both are acting downwards. So normal is mg plus f sine theta. So we replace this here. N is being replaced by mg plus f sine theta, which is equals to f cos theta, correct?
Oh, yeah.
Is that clear to you?
All right. Yeah.
So we have mu equals to mg plus f sine theta equals to f cos theta. Rearrange. So bring all the terms together, isolate mu, isolate f in this case because we need to find what is the force required to push, right?
Mm-hmm.
So isolate f.
Mm-hmm. Oh, and then you just sub in your values and you get it.
Correct. You get it.
Oh, right.
Now, when you get it, see in the denominator, you have cos theta minus mu sine theta. Do you see that part? And you calculate a value,
Yeah.
which is 33.4, right?
Oh, yeah.
Now, if you do the same thing, which I have
So
not,
mu comes in.
but that is an exercise for you. When you have pull, in that case, what happens? The formula here will be
Right.
equals to mu mg over cos theta plus mu sine theta.
Plus. Yeah, because it's going
In
upward.
the denominator,
Yeah.
plug in the values, calculate your answer. It will be lower, right?
Oh, yeah. So that's why it's easier. All right.
You get the idea. So I didn't do that
Get
calculation. I left it for you. So as an exercise,
I'll do
what
that.
you can do is
Yeah.
by how much is the force? By what percent is the force lower when you pull the car? You get the idea.
Okay. Yeah, yeah.
That's
So a bit percentage change. All right. Cool.
the only change will
So
be right here, right? This will be instead of plus minus because that force was acting upwards, right?
right.
Acting upwards, right?
As we saw from the diagram.
Correct.
Yeah.
So that was it. So that is how you're going to switch. So a small change which you make here for normal will help you write down this normal will be mg minus f sine. That is all
Mm-hmm.
for pull. And you can do the question. Is that clear? And what I want to show you,
Yeah.
since the denominator is more, the force will be lower. Correct?
Right. Yeah.
Perfect. So that is how, with the
And
help
then I
of
find the
small
percentage change.
examples, yeah, you can learn all the concepts. So, Amy, can you please summarize your learnings today?
I learned a lot. Like I said from the beginning, the whole of physics is not really my forte, but you made it very like straightforward, I think. This whole mu thing as well, the symbol, the definition, everything, I haven't heard it before. So yeah, so I actually really thoroughly understood it, especially with the whole cart. I like how you did it in different questions. You used the same example, but just tweaked it a bit here and there. So that was very clear. So yeah, thank you so much, sir. Yeah, I haven't even heard of this coefficient of friction or anything. So it all makes sense though, when you explained it, like logically it makes sense. From the frictional slope, how does it like not move? Like how do you keep it there when on a ramp? Because logically you would think if something's on a ramp, it's gonna fall down, but you're trying to find that minimum angle such that it would stay there. So yeah, that was really straightforward. And then the last question as well, super. Beautiful. So yeah, I think I got it.
Yeah, that's great. So try some questions from your book. Move on to the next unit.
Yeah,
now.
definitely.
You will get across mu and you'll learn much more. Share with me all the questions.
All right. Okay.
And then
yeah, definitely, sir.
Right? Have a great day.
All right. Thank you so much, sir. Yeah, you too. Thank you. Bye, sir.